I have to say I'm really happy to be here in this meeting. So thanks a lot for giving me this opportunity. As the title says, I'm going to speak about some really obscure point in Poisson geometry, and I'm not sorry for doing that. So let me start by explaining what those things are and why they are interesting, and then we'll get to what I actually want to do. So first, these bialgebroids and double symplectic groupoids. So where did they come from? So what was the motivation for those great masters for introducing such things? So these things, basically, they combine two sets of ideas. One set of ideas is Poissonly groups. Let's say. And then Lie bialgebras. So those are some very interesting Poisson varieties with algebraic structure, and as you would probably know, so these things can be described using Manin triples. So we would have like something which might be called Drinfeld double. So it's a Lie algebra with an invariant inner product with symmetric signatures. And inside we have two Lagrangian Lie subalgebras. And on this side, so what happens that then Poissonly groups come in dual pairs, one can say. So this is what came from Drinfeld and Semyonov-Janshansky, and it's somehow related to quantum groups. There is another set of ideas which is given by symplectic groupoids. So they were, this thing was discovered by Weinstein and Karasjov, probably maybe Zakrzewski, I'm not quite sure, independently. And the idea behind it, one can say it like this, that Poisson manifolds, they want to correspond to associative algebras. So we want to, our intuition is coming from mostly from imagining that this can be deformed to an associative algebra. So this is basically deformation quantization. But there is also like geometric quantization, even though it's like maybe well less developed, like fully finished theory, one can say maybe, which imagines that symplectic manifolds they are analogous to vector spaces. So this is more geometric quantization. And then any associative algebra happens to be also a vector space. So out of this, the thing was that whenever we have a Poisson manifold M, then there is actually a symplectic manifold with some additional algebraic structure, so which would somehow correspond to this associative product. So from there, one can then construct at least a local symplectic groupoid. Okay. And once this thing was discovered, and basically Poisson geometry became to much extent about Lie groupoids. And a natural question was, here there are groups with a Poisson structure, here there are groupoids, maybe with a symplectic structure. So can we somehow combine it together? So what is like some better guiding principle behind that? And So that led finally to those double simpler groupoids. And the thing was something like that you know, these Poissonly groups, they come in pairs, in dual pairs. Now, again, Alan Weinstein envisioned that the same thing would be happening for Poisson groupoids, polygroupoids with a compatible Poisson structure. So there's like one Poisson groupoid, another Poisson groupoid. They're over the same base. And then there is a common roof that would be a symplectic manifold, which would integrate this thing, this Poisson manifold, and also that Poisson manifold at the same time, but which would be a double. Okay, it would be a symplectic groupoid over this thing, a symplectic groupoid over that thing, and so this is a double symplectic.
Are you going to tell us, or is it irrelevant?
Oh, I can tell you. No, it's let's say, slightly relevant, one can say. That all those relations that, I mean, those submanifolds that we have there are quasi-tropic. As here, for the symplectic thing, all those relations are supposed to be Lagrangian, so the corresponding thing in here is quasi-tropic. It's one way of how to say it. There are other ways how to say it.
I'm sorry, I didn't understand that explanation.
Sorry?
When you explain me, what is, I still don't know what
Good, okay. So let's see, what is actually, maybe, let me use an invisible color. So if we have a groupoid, it should mean that we have a, whatever, this partially defined composition. So there is, I don't know, let me call it C. This is the composition. I mean, composition relation that this is, take somebody and compose it with somebody, and here we take the outcome of the composition. I'll put here bar, it just means that I'll take the minus the Poisson structure. Okay. And we require that this be quasi-tropic.
Oh, okay.
And the same for units.
Yeah. Thanks.
Quasi-tropic. Okay, and then the thing was finished by Curie, Mackenzie, and Ping-Shu, who introduced Lie bialgebroids. So this is here, over there is actually something which is called a Lie bialgebroid. Which is then a thing which somehow, it is a Lie algebroid and it integrates to a Lie groupoid, which would be this P. But its dual is also a Lie algebroid and that integrates to this thing. And okay, so this is Mackenzie, Shu. And okay, one way how to say what it is, that's one of the ways of their definitions is that if we take the Grassmann algebra, then this is a DG Gerstenhaber algebra. And maybe this was the point where somehow BG things entered Poisson geometry more seriously, one can say. So out of that, there was the development of courant algebras and I don't know what. So, but let me just stay here. And okay, so any further questions? Like, no, that's wrong. And let me give you an example, because this is a bit like an abstract story, but there is a very beautiful example coming from Liu and Weinstein. So this is called the Liu-Weinstein double symplectic groupoid. And this is simply what's happening in the case of Lie bialgebras, when the Lie bialgebra is actually a Lie bialgebra, meaning that when the base is just a point. So the case of a point, and yeah, A easily. So what do we have there? Oh, okay. It is just a point. Then those Poisson would-be groupoids are simply H and H star. I mean, as Poisson groups, 3 groups. If you wish, we have those 2 arrows, but they just go to the point. And who is here? So they gave a very nice explicit construction, which can be described as a moduli space of flat connection on something. I know that colors are invisible from there, so let me use them. So we will take our surface will be a square, so it's a surface with a boundary. And so here we take moduli space of flat, whatever. There was this double, okay, so D connections on the square. And since there is a boundary, we need to impose some boundary condition to make it symplectic, to make the Atiyah-Bott thingy actually work. And it's what we can imagine, that here we want this connection to take values in the Lie algebra of H. It's H, and here it's H star and H star. With the symbolic form is just the Atiyah-Bott thingy. And how is it a double groupoid? Well, you see that square, so it can be either composed like that or like this. With respect to both compositions, this is it's a symplectic groupoid. That's what we have. Sorry? If you take two flat connections I mean, the space is the moduli space of them. So let's take 2 points. Yeah. And so let's imagine that you have another square here. And if the holonomy here is the same as the holonomy here, so that's the condition for being composable, then we can just glue them together. And the same for the other side. If you wish, that's my favorite and very inconsequential picture. One can describe the composition also like this. That we take 2 of those. And instead of somehow gluing them, let's draw some cobordism. So this would be, it would be some kind of solid Y. Okay, this is colored in orange. And yeah, here on the other side, you can imagine that there is something happening. Okay. So this is like a solid Y where the front and the rear face are green and the other faces are orange. And ideological how one should see it is like with a cobordism in Chern-Simons theory with the boundary conditions. Okay, so this is some kind of very fake. Oops, sorry. Simons thingy. And yet another thing, like, so this is a symplectic manifold with some algebraic structures. So in this ideology, where to symplectic manifolds, one should assign assign vector spaces, which would be what is non-existent, probably Chern-Simons should be doing. So what is the vector space? The vector space is the corresponding quantum group. So it's like the symplectic version of, okay, U H bar H. Or H star, doesn't matter. I mean, they differ kind of by change of orientation in this world. So is it okay? I mean, most of it is ideology, so. Sorry?
Not clear.
What is not?
How do you get the quantum group?
Well, in some sense, you know, like, if we start with H as a Poisson manifold, and we integrate it to a symplectic groupoid, this is it. That's the symplectic groupoid. So the geometric quantization of this Poisson manifold should be the deformation quantization of the Poisson manifold. Therefore, it should be the quantum group. I'm not saying that this can be directly done with this Chern-Simons picture. I'm just saying that that should correspond to.
Okay, so by geometric quantization.
Yeah, but yes, by geometric quantization. So this is what I mean, the symplectic version of. Okay, is it, so now I can move, if this was sort of, okay, now I can move to what is that braided world. Maybe okay, so I didn't mention any differential graded manifolds, so let me just mention in passing that the same picture now works for arbitrary Lie bialgebroids, where we would take a DG maps from T1 of the square into the corresponding courant algebroid and have those boundary conditions satisfied. But I think this example is actually nicer than any general construction. So now we want to, the aim, move all of this to some kind of equivalent world. So where instead of Poisson manifolds, we would use what are called quasi-Poisson manifolds. Okay, I'll call it like G quasi. And symplectic. They are replaced by what are called G quasi-Hamiltonian. I will take some time to explain what those things actually are. But let me first say why would one do it, or what's a little bit behind. And if it doesn't make any sense, then it's perfectly okay. So first of all, this G is such that on the Lie algebra we have an invariant pairing. So one thing that if we have an invariant pairing, then we can basically talk about the corresponding quantum group, at least like in the sense of a quasi-Hopf algebra with an R matrix and everything like that. So this is what these things, those quasi-Hamiltonian manifolds, they are supposed to correspond to representations of that quantum group, and which is a braided monoidal category because of the R matrix. So this somehow is related to, if there was a geometric quantization for that, this is related to U, G, whatever, let me put a H like that, modules. Like the real way how to do it if you have an inner product is that we really take just modules of G, then we just introduce formal power series in H bar, and then we pick up a Drinfeld associator and thingies. But I will not give you all those details. There is just some nice braided monoidal category. So this is a braided monoidal category. These things, they will correspond to, well, associative algebras in the same braided monoidal category. This is yes, in exactly the same thing, just as before. But I will not be doing any quantization, so no worries. It will be pure geometry or a little bit of algebra maybe. And why would one ever do such a step? For one thing is that these things were introduced by, I will say the names in a moment, by people for the reasons of studying moduli spaces of flat connections. There are all these moduli spaces of flat connections over there, so it should be even better. No, after. So why? So one thing is moduli spaces. Connections. The second thing is, this thing is going to be a braided monoidal category, just as this quantum counterpart. It will be a very natural, even though pure geometrical braided monoidal category. And Hopf algebras, if you look at the definition, in generality, they want to live in a braided monoidal category. We're just missing out if we're forcing ourselves to what are vector spaces. We just don't see in everything what's going on. So this will be braided. Sorry. Of algebras. Is it enough, this motivation? No. So the third point is just, I don't know, why not? So, as it happens. Yes.
So in that picture over there, which is related to your motivation here. So if you take flat connections on a surface with boundary, you can make sense of what happens at the boundary as so the modular space is a symplectic manifold with a Hamiltonian action. So it's not, I don't see why you need to take quasi-Hamiltonian.
No, you'll see. I'm not saying that this is that. I mean, this is that when G is equal to 0.
So when you go higher, you really need to take quasi-Hamiltonian.
I mean, if I want to have anything braided, then I need to get that quasi or whatever. And now I should give you these definitions and what's behind them, and then I'll maybe get to some results in the end. Now, who is who? No. So at first I define what are those G quasi-Poisson things. So this is due to Alexeyev, then Anton Alexeyev, then Yvette Kosman-Schwarzbach, and then Weinrenken. Actually, those G quasi-Poisson models were defined after those quasi-Hamiltonian spaces, but this definition is kind of simpler. So let me just write those words. We will need probably like T in S2 G. This is just the inverse of the inner product. So just we put it into G in place of G star, and then so a G quasi-Poisson manifold. So what is it? It's M. I know it will look a bit random, but don't worry. It's M with an action of the group. Then we have a G invariant bivector field. And the final thing is that this G invariant bivector field is not Poisson, but satisfies something slightly different, such that when we take Schouten bracket with itself, then this is equal to 1/2 of, let's call this action rho. And so this should be a 3-vector field, so we need to have a 3-vector field on G. And so what thing we will have, we just have the structure constants where we raise the indices. So phi is in H3 G, these are basically structure constants. Yeah, to commentate it. So we take 1/2 rho of phi. For a suitable value of 1/2, I think this should be true. It's not difficult, it looks a little bit random. And there's another thing.
So what is Ro's the action?
Ro's the action, so I extended it to whatever multi-vector fields, just a shortcut notation. If you want to know some idea, or if you know all this story about associators or where this comes from, if you imagine that we quantize it somehow, then this associativity is in the Drinfeld category contains the associator, and so therefore also the first order term in whatever in the commutator probably this should somehow involve also the associator, and it does. So this is the leading term of the Drinfeld associator, but it's not necessary to know it's just this. And I'll give you examples in a moment, but the nice thing about this category is that you can get something out of nothing. That for Poisson manifolds, it typically doesn't work. You need to start with something Poisson to, okay, you can construct T star or something, but here there's a very specific way of getting something out of nothing. Namely, when you take product of two quasi-Poisson manifolds, it will again be quasi-Poisson. But even if those brackets, if those pi's are 0, the outcome might be non-zero. So this is what is called the fusion product. So fusion. So if you have whatever M1 and M2, G quasi-Poisson, that implies that if you take M1 times M2 is again quasi-Poisson. But what should we take? Okay, there should be a G action, so that we take just the diagonal G action, just the most interesting, natural thing. So we do diagonal action of G. but one needs to modify a little bit, there's some little twist how to get the Poisson structure. There is like this pi on m1 times m2 is defined to be like whatever, pi 1 plus pi 2, and then there is this mixture term. There is something like maybe minus, for a suitable value of minus, of maybe a row, something, tensor row, and we take this whatever, t1, 2, meaning that we put one leg of t on m1 and the other leg of t on m2, and there's some formula. And in this way, they form a monoidal category, non-symmetric, not braided.
So this doesn't become the Cartesian pi, because you change the structure.
So
So it's not Cartesian.
yeah, okay, it's not, I mean, here is Cartesian, just, I mean, this is...
What do you mean? So, like, I mean, if you didn't do that,
you have to do that. I mean, if you don't do this funny thing, then just the sum is not a quasi-Poisson manifold. It doesn't satisfy the equation.
but I'm just asking, like, this is also the categorical just products in this category or not?
Probably not.
Okay.
No, it's just, yeah, it's some natural thing to do. Actually, they expect it to be monoidal category because associative algebras in a braided monoidal category, yeah, when they form a monoidal category, we can still take the tensor product. So how does it work? If you have an algebra, so we take two things and another thing, and okay, if you have I know it's the same color from distance. So if you have another algebra, so this is the way how the tensor product of two algebras in a braided monoidal category becomes again an algebra. And you see there is this crossing here, and that crossing corresponds to this. It's like the first order thingy in this Dreamfeld's category or quantum groups or something. Just to give you some explanation, but again, one can stay purely within geometry. Okay, and then I should define the other thing. This was by a similar set of authors, Alexeyev, Malkin, and then can. So what is a G quasi-Hamiltonian thingy? It looks a little bit similar. So we have a action of G on M. We call it rho. We have a G invariant two form. So omega 2 M is G invariant. There is also a moment map, that's why it's quasi-Hamiltonian. So there is mu going from M to G. So it's like a group varied moment map we're taking that is in the same group, and which is G equivariant. Where the action on G here is by conjugation, so it's like what would one naturally expect. And such that, okay, here the definition is a bit longer, but it's not so bad. The first thing is that d of omega is actually not zero. It's the same-ish thing as here we have some kind of fault. So it's equal to mu star of eta, and eta is what were maybe one can call it the Cartan free form. On G, like both sides invariant, the natural free form which is there. There is some moment map condition that if we if you take, like plug in an element of the real algebra into omega, then I know this looks a bit maybe funny, but that it's 1/2, and we take we pull back the left plus the right invariant or right Morey-Cartan form, and then take the inner product with V. And finally, there is a non-degeneracy condition. And just to relate to that, I will say it in this way, that if you take omega and make it non-skew symmetric, we add there the pullback of that metric from G. So we take plus maybe 1/2 mu star of the inner product, which now is extended to live on the group. That this is invertible, and the inverse is then equal to pi plus something symmetric. So that's how one can go from here to there. So pi plus maybe there's 1/2 rho with t. So that's the symmetric part here. It looks terribly random, I know, but the main examples are very cute. They're coming from moduli spaces of flight connections. Where this omega will be given by some intersection pairing as it should be, but in some slightly funny way, so it will not give us a close to form. So main example is that we take a oriented surface with, let's say, one boundary component, sigma. We pick some particular point at the boundary, let me call it randomly x, and then we will take the moduli space of flat G connections, but where one can say where the gauge transformations are supposed to be trivial at this point x, or in other words, what we can say, we'll take home from pi1 of sigma based at x to G, or whatever is like H1 of sigma with relative to x, like non-abelian H1 with various in G, or modular space of flat connections on flat G bundles over sigma, which are trivialized over x. And what do we have on such a thing? When you have flat connection, we can now take the whole array along the boundary, and that gives us an element of G, and that is the moment map. So we do this. So mu is equal to the whole array over the boundary, where it's starting at x. And at this point x, we have still an action of G. One can say by those gauge transformations or by changing the trivialization at that point. So let me call it whatever some m sigma x G. What we're still missing is omega. So what what is omega? It can be given by intersection pairing. So, you know, with the tangent space at any particular point of that M. So what is going to be, okay, at some point P. So these are going to be, this is going to be the first cohomology of over sigma relative to X with values in the adjoint bundle. Add P on. And we would like to have an intersection pairing here, but the trouble is that we cannot intersect two such things when there is the same point on the boundary. What we could do, if you could split the boundary rather into two parts, and like taking relative to this part, and then we can intersect with relative to that part. So how do we do it? We simply we just do it, as I said. So we can, let's choose another point, y, for example, or let us simply split the circle into two intervals, two arcs. And what we have done is that at h1 sigma relative to x, and if we take it now the same thing but relative to y, so here we do have an intersection pairing. So if you want to think in terms of one forms, you take one form which vanishes on some arc and then multiply with the one form which vanishes on the complementary arc. And then whenever you need to use Stokes' theorem, it's fine because their product is zero on the entire boundary. But this space is not what we want, right? This is why, but what do? We simply turn the thing, only this, like the neighborhood of the boundary, turn it around a bit, and that's how we can identify this guy. This thing is isomorphic. If you choose the direction of turning, that's isomorphic with h1 sigma relative to x. That's it. This is a non-skew symmetric pairing. What is it? Is this non-skew symmetric nonsense that we saw up there. So this is omega plus, is there 1/2 or, I don't know, for some value of 1/2. 1/2 mu star that's inner product. Okay, I should get to this.
Omega here is what?
Sorry?
Omega here is
so this is how we define that. You know, I said that this is a example of a quasi-Hamiltonian space, yeah. And I said what is mu and what is the action, yeah. But I had to define omega, and omega is this pairing, except that this pairing is not skew symmetric, so omega is only the skew symmetric part. And okay, never mind. The final thing. So what is here in this introduction, basically? Now the fusion product in this setup. How does it work? Imagine that we take a disk with two holes. And now when we take two of those quasi-Hamiltonian manifolds, just imagine that there are those modular spaces. It's enough to get its intuition. We glue one of them onto this hole, the other one onto that hole. So that's how we define a new quasi-Hamiltonian manifold, which is simply the product of those two. But now it's actually a braided monoidal category. Because, yeah, one can turn things around. So there's an explicit formula for that, but this is some geometric explanation for the braiding, which corresponds to the braiding in the Drinfeld category in this quantum world. Okay, so this was like definition of everything. Now I have like maybe 5 minutes roughly. Yeah. So let me give you the results. So the first thing was about, as I started, about just Poissonly groups and Lie algebras. So what's happening here? So one can talk about G, quasi-Poisson groups. So what would it be? Well, it's simply you take a quasi-Poisson group, meaning that this is a quasi-Poisson map, and the product is a quasi-Poisson map. And these things are now classified or given by Manin quadruples. So are given so we have still a D real algebra with a pairing, but this is now split into 3 subalgebras, not just 2. And one of them is G, and the other one is H, and the last one is H star. It's just a split to as vector spaces, just as for Manin triples, and the condition is such that whatever H perp is equal to the other two, and H star perp is equal to G plus H. So this is a result with Friedrich Wallach, who just left. So what would be an example? We can take for D a semi-simple Lie algebra, and then we would, for this thing, we might take some parabolic thingy, parabolic Lie subalgebra. For this thing, we would take a whatever opposite parabolic Lie subalgebra. G would be simply the intersection, meaning the Levy subalgebra. So it's like whatever, maybe upper triangle, lower triangle, and diagonal, even though it might be block diagonal and block things. Now the second thing is, this would be those symplectic groupoids. So this is something which we did before with David Leblanc. So this was with Leblanc, which says that if M is G quasi-Poisson, then T star of G, so of M, sorry, is naturally a Lie algebroid. And if integrated, we get something which is naturally called, can be naturally called a G quasi-Hamiltonian groupoid. And integrates. G quasi. And now, okay, the third thing, like how to combine those things. So there is a way how we can define G, whatever, quasi-Poisson, I don't know how to put it, G quasi bialgebroids. And there are several ways of doing it, but one possibility is to use these kind of Manin quadruples, where now D is a courant algebroid. Like, for example, and then the outcome is that they can be integrated to whatever double quasi-Hamiltonian groupoids. Oh, can I still take 1 minute, or I shouldn't maybe? There is a little bit of fine point here. This double groupoid, we are now in a braided monoidal category. So we need to take care of how to move things into the right place. So it's fine as long as you say that one composition is horizontal and the other one is vertical, and that we're always moving things, rotating them to the right position. And maybe finally, so what would be a picture as we had before with those modular spaces of flat connections? So, moduli. So now we take a disk with a mark point outside, and there will be some kind of there will be some what were the domain walls, or how to put it. So here we have a flat G connections. Here we have flat D connections. And the way how they transit between this and those is that on the boundary we have one of those P's and P, whatever P stars. So here would be like P, P, P star, P star. Okay, and to glue things, you plug them into those holes, then you rotate them, and it works. Yes, so as I said, it should be a particularly obscure corner of Poisson geometry, and I think I perfectly succeeded. So thanks a lot.